Our goal is to build an agent that can ingest raw video, apply step-by-step logic to the events on screen, and trigger a response. We are going to build this autonomous visual system locally using the Gemma 4 open models. To prepare your local environment, you need to install or update 3 specific Python libraries: Transformers, Torch, and Accelerate. These dependencies allow you to run complex multimodal workflows entirely on consumer hardware, removing the need for external cloud APIs. Step 1 is selecting the right model size. This decision is dictated by the specific memory and compute limits of your local hardware. Google DeepMind designed the lightweight E2B and E4B dense models using per-layer embeddings. Instead of increasing the total parameter count, each decoder layer uses its own small embedding for token lookups. This table shows the efficiency. E2B has 5.1 billion total parameters, but its effective count is 2.3 billion. Contrast that with the 26B A4B Mixture-of-Experts model. It contains 25 billion parameters, but activates just 3.8 billion to maintain high speeds. The selection rule is simple. Deploy the dense E-series models for mobile phones or edge devices, and use the MoE model if you have a workstation with a consumer GPU. Choosing a model based on its effective or active parameter count is the key to running frontier-level AI on restricted hardware. To process memory carefully, we begin by taking the video file and extracting exactly 1 frame per second. We control the memory footprint of these frames by configuring the visual token budget. The budget defines the resolution. A 1120 token budget captures fine details for OCR, but requires significant compute. A 70 token budget allows broad visual analysis with minimal memory. For sequential frames, set this to 70 or 140 tokens. Restricting the token budget is what allows a local machine to process lengthy video sequences without exceeding its physical memory. Next, we construct the prompt array by combining the optimized video frames with our text instructions. The order matters. Place all image and video content before your text instructions to ensure the model correctly contextualizes the visual data. We then activate thinking mode to force the model to reason about those frames before it attempts to answer. To enable this, insert the control token at the absolute beginning of your system prompt string. Note that in multi-turn conversations, you must strip the model's previous reasoning steps from the chat history before you start the next turn. Using the correct modality order and the think token provides the logical foundation for visual analysis. To make the agent actionable, we define a Python tool, such as a script that triggers a security alert when it detects specific movement. With thinking mode active, the model separates its internal reasoning from the final instruction it sends to that tool. In this terminal output, you can see the structure. The model writes its logic inside a channel thought block. Once it reaches a conclusion, it closes that tag and outputs a structured JSON function call. Our script parses this response, logs the thoughts for review, and routes the clean JSON data directly to the tool's execution function. By programmatically parsing this thought action structure, we can use the model's reasoning to drive local functions. We can now execute the final script. The autonomous agent ingests the video frames and initiates the analysis. The terminal shows the reasoning process as it unfolds. When the agent identifies the target event in its reasoning block, it generates the JSON string and triggers the security alert. This architecture is flexible. You can deploy the dense models onto mobile devices or utilize the audio processing capabilities unique to the E-series variants. You now have a functional, hardware-optimized visual agent that operates entirely on your local machine.
Please like, share, and subscribe.